Standard logic gates process inputs and immediately forget them. To build complex digital systems, we need circuits capable of trapping and holding a binary state. The baseline memory element for this task is the SR, or set-reset flip-flop. It is a level-clocked circuit built from cross-coupled gates, featuring a set input, a reset input, and two complementary outputs, Q and its inverse, Q bar. Its operation relies on specific input pulses. When the set input is driven high during a clock pulse, the signal propagates through and the Q output becomes a 1. Conversely, when the reset input is driven high during the next clock pulse, it forces the Q output back to 0, and Q bar returns to 1. The SR flip-flop effectively holds a bit of memory, but it operates under a strict architectural assumption. The outputs must always be opposites. Breaking that rule breaks the circuit. That rule is broken if the system receives a command to drive both the set and reset inputs to 1 at the exact same time. When both inputs are high, the logic gates attempt to process the command simultaneously, forcing the circuit to try and output the exact same logic level for both pins. This creates a direct contradiction. Q and Q bar are structurally designed to be inverses, but the circuit is now being instructed to make Q equal to Q bar. As the clock pulse ends and the input signals drop, the logic gates race to resolve the conflict. The hardware will eventually settle into a stable state, but it's impossible to predict whether Q ends up as a 1 or a 0. Because this forbidden state produces unpredictable output, the standard SR flip-flop requires a structural modification to prevent conflicting inputs from ever reaching the output gates. The engineering solution to this vulnerability is the JK flip-flop. To prevent contradictory inputs, the architecture modifies the SR design by adding cross-coupled feedback loops. First, the inputs are renamed J and K. Then, a physical wire is routed from the Q bar output all the way back to the input gate for J. Simultaneously, another feedback loop routes the Q output back to the input gate for K. This wiring alters how the circuit processes information. Instead of blindly accepting any input signal, the current output state now acts as a gatekeeper, determining which new inputs are allowed to enter. By making the inputs dependent on the existing outputs, the architecture prevents the signals that would lead to a logical contradiction. This table shows the operation modes for the active-high JK flip-flop. It retains standard memory functions. When both J and K are 0, a clock pulse has no effect, resulting in no change to the output. When J is 0 and K is 1, the circuit mimics the old reset behavior, driving the Q output to 0. When J is 1 and K is 0, it acts as a set command, driving Q to 1. Across these three conditions, the JK flip-flop performs identically to the baseline SR model. The test is how this architecture handles the previously forbidden state, where both J and K receive a high signal simultaneously. Assume the current state of Q is 0, meaning Q bar is 1. Because Q bar feeds back to the top gate, its high state keeps the J gate active. The Q output feeds back a 0, which entirely disables the K gate. When the clock pulse arrives, the high inputs can only enter through the active J gate. The signal passes through, executing a set command and flipping Q to 1. Now the circuit is in the reverse state. The Q output is 1, feeding back to enable the K gate, while the 0 from Q bar feeds back and disables the J gate. If another clock pulse arrives with both inputs still high, the signal is forced through the K gate, executing a reset command and driving Q back to 0. The feedback loops have replaced the forbidden state with toggle mode, a condition where the circuit flips its output value on every clock pulse. On paper, the logic of the JK flip-flop is sound, but physical hardware introduces a variable that pure logic ignores: time. Every physical logic gate has a propagation delay, or delta T. This is the time an electrical signal takes to push through the transistors and output. We also have to account for the clock pulse width, or T sub p. This is the total duration that a level-triggered clock signal remains high, holding the gates open for data to pass. In level-clocked systems, the duration the clock remains high is often significantly longer than the time it takes for the logic gates to process the signal. The JK flip-flop's logic assumes state changes are instantaneous. By placing it inside physical hardware that requires time to operate, we expose a vulnerability. This diagram illustrates the physical timing mismatch during the toggle state, where J and K are both 1. When the clock goes high, the gates open. After a brief propagation delay, the circuit processes the inputs and the output toggles. But because the clock pulse is still high, the new output state instantly feeds back to the input gates, is processed again, and forces a second toggle. Because the physical processing time is so much shorter than the open window of the clock pulse, the circuit rapidly and continuously oscillates between 0 and 1. This rapid, uncontrolled feedback loop is known as the race-around condition. It is a physical breakdown of a logically sound circuit. This oscillation continues for as long as the gates are open, only stopping when the clock pulse finally drops low. Because the switching happens in nanoseconds, the final state of Q is completely unpredictable. It becomes a game of electronic roulette, dependent on the exact moment the clock cuts off. To prevent the race-around condition in level-clocked systems, the circuit must follow a strict rule. The clock pulse width must be strictly less than the propagation delay. Manufacturing hardware with that level of timing control is difficult. Instead, modern engineering solves this by upgrading the architecture to edge-triggered or master-slave configurations that limit data entry to the exact moment the clock transitions. The JK flip-flop resolved the SR forbidden state by re-engineering the circuit's physical structure. It serves as a reminder that digital logic is never purely mathematical. It is always subject to the physical laws of time.